Hello friends, and welcome back to another episode from Annie's Arms. Today's video is really the first in our series on how to lubricate your firearm like an engineer. I've been trying to lay out this series in my head and make sure that it's methodical and organized and easy to understand, and I thought the best place to start would be a little more of a fundamentals video. So what we'll be talking about today are key concepts and vocabulary that I think are going to be important for the future videos. I want to try to focus on the what, why, and how, and we need to have some building blocks to do that. To begin with, you may be looking at this picture and thinking, what does a bar of soap have anything to do with this? And we'll talk about that later in the lubrication section, but a bar of soap and how you lubricate your firearm or your tractor have more in common than you probably ever thought before. So to begin today, we need to understand what is lubrication. Lubrication is the process or technique of reducing friction between two surfaces. Another word that's also often used in conjunction is the word tribology. Tribology is the science of understanding friction, wear, and lubrication. So with those two words and an understanding of what they mean, I want you to think about, should I call this series Lubricating Your Firearm Like an Engineer, or Understanding the Tribology of Firearms? Feel free to add your thoughts in the comment section, and we'll see if a name change is actually justified. The first place we're going to start is friction. So what is friction? Well, friction is the force that acts opposite the direction of motion. And so, with that, how do we calculate that? Or I guess maybe the better question is, what is that? So we have our two blocks. We have our red block. We're going to apply a force, and the block will move. The friction force is actually acting in the opposite direction. That is the force we have to overcome to get the block to move. So we know we have a force of friction, and in engineering, we like to calculate things. So our friction force equals our coefficient of friction, which is the Greek letter mu, times our force in the normal direction. So our force in the normal direction is the force that's acting on the body. So that could be the weight of the block. It could be an added force, due to acceleration. And another way that we could get a normal force would be in a bolted joint. So that clamp load that the bolt puts on the two bodies also results in a normal force. So to calculate the friction force, the force that I have to overcome, we need to know our normal force and the coefficient of friction. So where do we find that coefficient of friction? In modern day, we can use AI, or we can go back to our old faithful textbooks. So here we have the machinery handbook, and on page 158, it lists some common coefficients of friction for static, so steel on various materials, or static on various materials, aluminum on aluminum, silver on silver, so on and so forth. We have a coefficient of friction for a clean, dry surface, as well as a lubricated surface. Where we can also look for coefficients of friction is another textbook called the Mark's Handbook. In the Mark's Handbook, we again have materials on different materials. We have our static coefficient of friction, again, clean and dry, greasy, lubricated. But we also have this sliding coefficient of friction. What's important to understand is the coefficient of friction can change, or does change, from static, a velocity of 0, to a velocity of something. And once that body is moving, the coefficient of friction reduces. What's also important to note here is our coefficient of friction is unitless. That's important when we look back at our equation. So we have our friction force equals unitless coefficient of friction times our normal force. Our normal force is normally going to be units of either pound force or newtons. So that times something that is unitless means our resultant is going to be in pound force or newtons. Why is that important? Well, we don't have contact area in the equation. So whether I have the highest amount of contact between the two bodies, a lower area of contact between the two bodies, or the lowest area of contact between the two bodies, that force to move the object does not change. And that can be a tricky concept to grasp. One last thing worth noting before we move on, because you might not have seen it, is if we go back to our coefficients of friction for static and sliding, we'll see that they actually experimentally determined it for different lubricants used. They did this again for the static and the sliding coefficients of friction, but we can see how those coefficients of friction change based on different lubricants. So the important takeaway that we're trying to stress in this series is also all lubricants are not created equally, and so we can see that here in the coefficient of friction. Wear is the next thing we're going to talk about. Wear is the removal of material that is unintentional. The unintentional is important because here we have one of my MP5 mag tools. We removed material to get the shape, form, and function that we need for the mag tool to work. And most people would not refer to a machining operation as wear. So the four common types of wear are abrasive wear, adhesive wear, corrosive wear, and surface fatigue. Abrasive wear can take place between either dissimilar metals or dissimilar materials or similar materials. You need a third party in the middle, and common third parties would be sand and dirt. So as you have the relative motion between the two bodies, the sand or dirt is what's creating high stresses on the surface contacts between the two and causing material to be removed. Adhesive wear can also take place between similar or dissimilar materials. There, at the surface interface, you can have atomic bonding or cold welding that removes material from one body and transfers it to the next. when that material is removed, it is possible for that cold welded or atomically bonded material to then break off. So your adhesive wear can then lead to abrasive wear. Corrosive wear is less common today, but it is still a problem. Firearm manufacturers have spent a lot of time and a lot of money working on different coatings and treatments to help keep corrosion and rust away. Another type of corrosive wear is what we call a galvanic couple. Galvanic couples can happen between dissimilar metals, and aluminum and steel are very common. You need an electrolyte in the middle, but you create a galvanic couple and the aluminum will slowly be eroded away, but the steel will be left in place. This is a larger problem in the automotive and aerospace industries, and less of one in our firearm space. Surface fatigue is the last one. Surface fatigue would come up typically in a bearing race, and what you would see are little pit marks on the contact area where the balls or the rollers of the bearing element have been rotating. What causes that are high stresses, and those high stresses are resultants of either discontinuities in the surface of the bearing race or in the matrix of the metal itself. So as that bearing is loaded and as it's rotating, those stresses are exceeded, and then material is removed. It is fatigued from the surface, and that would then show up as pitting in the bearing race. The common ways for dealing with abrasive wear and adhesive wear are hardening the surfaces and having a quality lubricant between the two. Corrosive wear can also be helped with corrosion inhibitors in the lubricants, and surface fatigue is really a function of design and the material properties that you're working with. The next thing we're going to talk about is the meat and potatoes, and that's going to be lubrication. So for lubrication, we have many types. Most of you are going to be familiar with our liquid lubricants. We then have our grease lubricants. We also have solid lubricants like Teflon. And then there's a fourth one that's often forgot about, and that's actually air. There are bearings in industrial machines that are supported by air. So it too can act as a lubricant. So some of the solids that we have would be Teflon, molybdenum disulfide, tungsten disulfide, graphite, and there's probably at least a half dozen other ones that I'm at least not thinking about at this time. So we're going to start with our liquid lubricants. So with our liquid lubricants, we're going to use a quart of oil to help explain some of the key bodies that are important. So first, we have the API, American Petroleum Institute. And so we can see that on our motor oils by what they call the donut here in the lower corner. The next governing body would be ISO, the International Organization for Standardization. So they help set some of the testing standards and specifications. We have SAE, the Society of Automotive Engineers. We have ASTM, American Society for Testing and Materials. So they also, kind of like ISO, set many of our testing standards and requirements. And then we have ILSAC, the International Lubricant Standardization and Approval Committee. And you might not have seen it before on the back of an oil jug, but there we can see we also have an ILSAC rating. So those are some of the larger players when it comes to defining our lubricants. There's going to be some other ones that I didn't mention, but those are going to be the important ones. So for our liquid lubricants, what's often not discussed are the base oils that make up these liquid lubricants and how they fall and how they're categorized. Here we have API's table of our 5 groups for base oils. Groups 1 through 3 are what come from crude oil, our dead dinosaurs. And groups 4 and 5 are what are generally considered our fully synthetic base oils. In the automotive space, however, group 3 oils are also classified as fully synthetic. And so I want that to sink in for a minute, that when you're buying an engine oil that says it is a fully synthetic API SP engine oil, it can be manufactured from any one or any mix of these 3 groups of oils. If you're buying a conventional engine oil, it's more typically going to be a group 2, and I believe some of the gear oils are actually made from group 1 base oils. So thinking about these 5 groups and how they differentiate each other, one way to think about it is how they've come about through time. So our group 1s were developed first because the refining process for the crude oil was cruder, pun intended. And then as we've progressed and learned more about the refining process and how to get the properties out of the crude oil that we want, we've progressed from group 2 to group 3 and then a fully synthetic PAO. What's also important to understand as we transition from a group 1 to a group 4 is it's also a definition, or it helps to understand what's actually changing. So for our crude oil, if we go back to our beautiful chemistry and technology of lubricants books, the components of crude oil, we have our alkanes, which are our paraffins, alkenes, I'm not going to try to say that one, but its common name would be naphthenes, and then our aromatics. So our crude oil is comprised of those 4 parts. And during that refining process, we're trying to make the oil more paraffin-based. Maybe the word paraffinic would be the right word for that. I'm not entirely sure. But we're really polishing that structure to be more paraffin-based and less of those other 3. So you might be asking yourself, what does it mean to be more paraffin-based? So the structure of a paraffin is we have a polar head, and then we have our hydrocarbon tail. And the alkenes and the aromatics and the naphthenes all have their own structure. So this is the base paraffin structure. PAOs, so as we transition to group 5, or group 4, my apologies. So group 4 is as pure of a paraffin-based structure as you can get. What also typically happens during the refining process is we get thinner viscosities. So our group 1s are typically going to be a thicker viscosity than our group 3s. And what's unique about our group 4s, our PAOs, is we're able to customize that chain length. So depending on how long the chemical reaction takes place when we're creating our PAOs, we can adjust how long that chain is. And by adjusting how long that chain is, we can tune the viscosity for the application or the chemistry that we're trying to get. So I've said a word a few times now that you're probably familiar with, but you might not understand what it actually means. And that word is viscosity. So viscosity is the measure of a fluid's resistance to flow. So we can have something with a high viscosity, like honey, and we can have something with a low viscosity, like water. In our engine oils, we can see the viscosity defined in two ways. Our 5W30 is actually telling us a lot about the viscosity and the type of viscosity that we're measuring. So the 5W is actually the absolute viscosity of the oil, and that's what we use to define the cold temperature performance. The 30 is what we call the kinematic viscosity, and that's how we measure the oil's hot temperature performance. So what are those, and where can we see those? So here we have SAE J300. In SAE J300, we have our limits for viscosity in both kinematic and then absolute. So here for a 30 weight engine oil, we can go across and it's going to have a kinematic viscosity of no more than 12.5 centistokes at 100 degrees Celsius and no less than 9.3 centistokes at 100 degrees Celsius. For our 5W side of the oil, we're going to have an absolute viscosity at minus 30 degrees Celsius of 6,600 centipoise. So notice we had a unit change between our kinematic and our absolute viscosity. So what do those values mean and how are they measured? So the kinematic viscosity is really kind of the easy one. And so we have ISO and I guess it's SAE. SAE engine oil. So ISO, they measure the kinematic viscosity at 40 degrees Celsius versus an SAE engine oil, we measure the viscosity at 100 degrees Celsius. The way it's done is you have a known volume of the lubricant or the liquid that you're trying to measure, and you flow it through an orifice, and you measure the amount of time that it takes for that fluid to flow through the orifice. And based on that time, that is how we establish the viscosity. The only force acting on that fluid is gravity. So its density plays a role in how it flows. That density is going to affect the force. For absolute viscosity, flowing any of these at these very, very low temperatures, it's going to have a fairly high time domain. So the way the absolute viscosity is measured is you have, again, a volume, you cool it to the temperature, and then you place a disc or a rod into that, and the disc or rod is rotated. And the torque or power that it takes to rotate the disc or rod is how we establish its absolute viscosity. So we're going to go back to our base oils for a minute, and we will circle back to the viscosity topic. So we kind of started talking about our group 3s and how we're becoming more paraffin-based as we transition between them up to group 5. What we skipped over are our group 4s, and what we skipped over were our group 5s. Group 5s are considered fully synthetic, but they also contain a crude oil-based lubricant or oil, which is our naphthene-based oils. If you remember here, as we're refining that oil, we're actually pulling the naphthenes out. But a naphthene-based oil does have a place, and it falls underneath a Group 5 base oil. We also have our esters, our PAGs, our silicon oils, as well as vegetable oils in this Group 5. So Group 5s are really more of a catch-all versus our Groups 1 through 4 define a little bit more about the structure. And so to highlight how broad this Group 5 category is, we can come back to Chapter 2 of Chemistry and Technology of Lubricants. This is our chapter on synthetic base fluids. We start on page 35. We actually begin with our PAOs, our Group 4, and then we really start transitioning into our Group 5s. And it stops on page 72 is our last page where we talk about our synthetic base oils. So it's a little under 30 pages of the different chemistries that are in there. And then what's nice is for each of these chemistries, it also talks about the applications where those chemistries are really best suited and where industry has kind of fallen on their uses. And so as a consumer, that's one of those areas where I started to feel the most frustrated as I started to understand that better. That when you're buying a product and it says fully synthetic, whether it's an engine oil, whether it's a gun oil, whether it's a hydraulic oil, nobody's really telling you which of the groups of oils are used or which base oil is being used if it is a Group 5. So we're really held in the dark, and it's not clear what manufacturers are really using the best base oils to get the best performance out of that base oil for the application that it's being used for. So that was difficult for me, and that's still one of the things and why I'm now on this mission, is to try to understand that better and bring a little more transparency to at least the firearm space. So the next thing worth talking through, as we look at this table, we can see this thing called viscosity index. So viscosity index is another way that we differentiate Groups 1, 2, 3, and 4. What is viscosity index? So, going back to our paper here. So viscosity is a measure of the fluid's resistance to flow. We can plot that on an XY graph, and we can have our temperature on the x-axis and viscosity on the y-axis. So down here, you would say have a viscosity of 0 centipoise, or centistokes, sorry. And then at the top, we'll say 2,000 centistokes. When this is plotted, we plot it on what we call the log scale. And viscosity is more of a curve, but when it's plotted on the log scale, it looks like a straight line. And so what we have is, as the temperature increases, our viscosity decreases. So as it gets hot, it flows easier. And honey and a glass of tea is an easy example to visualize there. Viscosity index is then a measure of how flat that viscosity decrease versus temperature is. So here, again, very crude examples, but this line could be representative of a viscosity index of 80. It loses more viscosity over the same temperature range. And this line could be representative of a viscosity index of 120. It loses less viscosity over the same temperature range. This is a cruder definition. There is a deeper definition behind viscosity index. More fundamentally, it's also a reference against two different types of base oils. And so they defined early, 1900s-ish, they defined one base oil as having a viscosity index of 100, and then I think they defined another base oil as having a viscosity index of 0, and then you're actually ratioing the difference between the two. But for simplicity's sake, viscosity index lets you know how flat that line is. And so what we can look at next are a more realistic representation of what a viscosity table, if that's going to be the right word, would look like. So earlier we mentioned ISO, our International Organization for Standardization, and they have different base oils defined by their viscosity. So this topmost line, again, it looks linear, but if you look over here on the y-axis, our scale is in the log scale. We have an ISO 1500, and then down here on the low side, we have an ISO 7. And so earlier, remember I said for ISO viscosities, they're defined at 40 degrees Celsius. So we can follow this 40 line up, and where it hits our ISO 7, if we go across, lo and behold, it comes out at 7 centistokes. Again, if we go to our ISO 1500, we find our 40 centistoke line, see where it crosses, and again we have a viscosity of 1500 centistokes at 40 degrees C. So what we can also see here is how the viscosity changes with temperature. So if we were to just, how do we want to look at this? Go across and find an oil with a viscosity of 50 centistokes. We could do that with an ISO 7 at approximately minus 10 degrees Celsius, or we can have that viscosity over here. What line is this? That's an ISO 150, and looks like that's going to be around 65 degrees Celsius. So we can have the same viscosity at different temperatures with different base oils. You may be asking yourself now, how do all of these viscosities that you're talking about compare to one another? We just looked at an ISO viscosity table. We've seen on our engine oils how we have different viscosity measurements there. We can look at our gear oils and see how we have different viscosities there. How do they all line up? How do they all compare? So this is a table where we have our different names of the oils with their kinematic viscosities. And we again have the ISO, where they're measured at 40 degrees Celsius, and then more of the SAE, I would like to think, American Gear Manufacturer Association, they also do it at 100 degrees Celsius. So here you can glean a little more on how an ISO 100 is actually pretty similar to an SAE 30. What you also might have seen if you work around industrial equipment is, an ISO 32, an ISO 46, or an ISO 68 dealing with hydraulic fluids. This may also be labeled as like an AW 46, an anti-wear 46. So this table lets us compare the ranges and the different names for the oils. All right, one of the last things that we're going to discuss, we're going to go back to our API oil groups. On more than one occasion, when I've been talking with my firearm friends, this oil seems to come up a lot. And there seems to be a general consensus out there that REM oil, it's just mineral oil. And mineral oil can mean many things. Baby oil is just mineral oil. We can look on the back, and if I can get everything to zoom right, ingredients, mineral oil, and fragrance. Mineral oil can also be some generic, conventional engine oil. It is also mineral oil. So when people throw around the word, that's just mineral oil, it can mean a very wide range of things. I have no problems running or rubbing baby oil on me. I'm not exactly going to take a bath in motor oil. But they're both really mineral oils because they are derived from our petroleum base stocks. So how they're refined to the level of refinement and the additives that are then placed in that mineral oil are going to then help define what the application and what the chemistry is, or maybe a better way of saying it, the application, if it's going to be a motor oil, it's going to be refined and have different additives included than if it's going to be a product that we're going to use either internally or on our skins. So for me, anyways, that's one of my personal pet peeves. Everything is not just equal. And when we lump things into a very large bucket, it's not clear and it's not helpful for anyone else. Another thing worth understanding is not all crude oils are created equally either. So here, in a generic sense, the variation of crude oils between different sources. So going back actually to this table, we can see the saturate level and the sulfur level also help define the type of oil or the group of oil that you're working with. So here we see different geographic locations: North Sea, Indonesia, Venezuela, and the Middle East, and the properties on a generic level that the crude oils that were extracted have. So the North Sea, that has a very low sulfur content compared to the crude oil that's often got out of Venezuela. The pour point, so the lowest temperature at which the oil is pourable. I know there's a little more refined definition for it than that. Crude oils that we get from the North Sea, pour point of -3. Crude oils that we get from Indonesia, 30 39, 40 degrees Celsius. So those two are very, very different crude oils. So the reason for that goes back to what our crude oil is made from: the paraffins, the olefins, the naphthenes, and the aromatics. So the different crude oils have different ratios of these base components, and that's going to dictate the base properties of the oil. And so different oils are extracted from different areas on the globe based on these, and they're refined into different base oils or categories of base oils, kind of because of that. So again, in the United States, or at least in the circles that I've ran in, there's often the conversation of, oh, well, we've got plenty of oil to do XYZ in the States. Why are we 1, 2, 3 on another global location? Well, some of it comes down to the quality and the type of crude oil that you have and what you're trying to turn that crude oil into. And so I thought this would be a good example of that. If your head's spinning yet, I promise we are almost done with our base oil conversation. So here we're going back to this table where we can see the different types of oils that we would be most familiar with. Kind of our hydraulic oils, our engine oils, our gear oils. All of these industries have focused on the viscosity of the oil being the primary definition of where that oil's going to be used or how that oil should be applied. A manufacturer may specify a hydraulic oil of an ISO 46. Your car may define an engine oil of a 0W20, and your rear end in the vehicle may define a gear oil of an 80W90. Yet in the firearm space, we just talk about oil and CLP. We're not defining the viscosity, despite the fact all of these are mechanical devices and machines manufactured to tolerances, and their performance is a function of the viscosity of the product used. So I'm trying to stress a little bit and try to start turning the conversation in our space away from I use a CLP or I use a generic oil, and try to get it turned to the product I use has a viscosity of 70 centistokes, 150 centistokes, or 10 centistokes. 10 centistokes, sorry for mumbling. Because the viscosity is important, and I believe if we start looking at our products that way, we're going to be able to get more performance out of our firearms. I'll go into this more when I actually have my focused video on firearm oils, or at least oils. And part of what I want that conversation to turn into would be a gentleman in, say, Alaska saying, I use an oil with a viscosity of 7 centistokes, and a gentleman in Florida may be saying, I use a viscosity or an oil with a viscosity of 100 centistokes. There's reasons behind those numbers, and I'll go into that in the future video. The last graph, I promise, that we're going to look at is called the Strybeck curve. It looks like my camera is having a hard time focusing. There we go. So this is the Strybeck curve. It helps define what type of lubrication we have. There's 3 kinds: boundary, mixed, hydrodynamic. Boundary lubrication, if we think back to the machinery or the Mark's handbook, is the lubricated friction. There is a layer of oil but for the most part, our bodies are in full contact with one another. As we move to mixed, now we're actually getting some of that body separation as we get some movement between the two. You're now riding on a little layer of oil, but you still have some asperities contacting one another. Asperities, the little peaks of both sides, are still going to be hitting each other a little bit. And then we have fully hydrodynamic. There, both surfaces are riding on a cushion of lubricant. So how do we get from the far left side of the graph to the far right side? Well, we can do that by either changing the speed. As we increase the speed, we get more into hydrodynamic. And a way to think about that is a water skier behind a boat. When you're first starting out, you're very much in the water. And when you're at full speed on the skis, you're really riding on the water. So speed is one way to do that. Viscosity is another way. So as we increase our viscosity, we're going to be moving from the left to the right. Our load is the third thing. If we decrease the load, we move from the left to the right-hand side. In our firearms, we're not doing much for speed or load. We can tweak it a little bit with springs and powder charges, but for the most part, we're not doing that. The biggest knob as a consumer to help ensure we're in hydrodynamic lubrication is understanding the viscosity of the lubricants that we're using. So for me, I started this hunt and I'm still going down it, but I want to find partially the highest viscosity lubricant that still gets me the performance that I need. And so in many things we think more is better, but we can extrapolate this curve and we can see we have friction, coefficient of friction on our y-axis. If you get too much viscosity, you also now start to increase your friction. So want to find that balancing point of being low friction and fully hydrodynamic so that we get the best performance. So our next topic that we're going to talk about is grease. Just like we started with the liquid lubricant section, the main body or governing people that we need to be aware of here is NLGI, so the National Lubricating Grease Institute. I believe they're a global organization. I don't think they're just here in the United States. So what is grease? So grease is actually composed of three parts: a thickener, a base oil, and additives. The thickener makes up about up to 30% of the grease. The base oil makes up 60 to 90% of the grease. And then additives can make up 0 to 10% of the grease. I didn't talk about it in the last section, but our typical motor oils and hydraulic oils. So with those lubricants, there you can have up to 70 to 90% base oil, and probably even there's some with 100% base oil. But you can have then between 0 and 30% additives in those different engine and hydraulic oils as well. So additives are always a very important part of our lubricating products. So back to our grease. For the thickener, you may be asking yourself, well, what is the thickener? So the thickener in our greases can be soap-based or non-soap-based. And so you might be giggling to yourself a little bit right now but the same chemistry used to make a soap is the same chemistry that we use to make the thickeners for some greases. The way the chemistry works, if you remember high school chemistry class, there is a reaction between an acid and a base. And when the acid and the base react, the resultant is a salt plus water. When a fatty acid is used in that reaction, the resultant is called a soap plus water. So to make literal hand soap, you would have an animal fat or oil, and you use lye. And so lye is a sodium or potassium hydroxide. So we use our fatty acid from the animal, and we use our base to then create hand soap. For a lithium grease, so lithium greases are the prominent greases here in the United States. So for a lithium grease, you would react a 12 hydroxystearic acid plus a lithium hydroxide monohydrate, so that's your base, and then the resultant is a lithium 12 hydroxystearate, which is the grease thickener, plus water. And so during the grease manufacturing process, that water then has to get boiled off to make a pure thickener. So here we have a pretty handy table that shows us the prominent greases. So here we have our soap thickened greases, and we have our non-soap thickened greases. The other thing to understand with our soap thickened greases is we can have two types. We can have simple soaps and we can have complex soaps. There are some nuances to a complex soap, what the word actually means, and what you actually have. So lithium complex soaps are not true complexes. If you talk to a grease guy, depending on where he falls, he may give you a very long education on why that's not actually a complex and how annoyed he is by you calling it a complex. It is more of a marketing term for the lithium soaps, and I'm not an exact expert, but there are some of the other ones where you do have a truer complex as far as how that word is used in chemistry and what it means. But the basic way of understanding the difference between a simple grease and a complex grease, because you might see that at the store, is a complex grease has more inner linkages in the matrix. So if you think about the thickener, the soap, as a sponge, a simple soap is going to have fewer cross-linking between the spongy materials. It would be a little softer, would be a way to think about it. It would be potentially a little more porous, would be a way to think about it. And a complex soap would be a higher density, sturdier sponge. It's going to have more links between the elements that make up the sponge, which then make it more durable. As you're wringing it out, as you're squeezing it and, through the different working cycles, it would be a heavier duty, more durable sponge. So it's not a perfect definition, but it's at least a way to visualize and understand simple soaps versus complex soaps. These are our non-soaps. They are all a little different. So we've got polyureas, calcium sulfonates, standard silica, organo clay, PTFE, so Teflon, and then carbon black. So these all have, as you can see in the table here, different pros and cons, and when I do my more focused grease lubrication video, I'll go deeper into the pros and cons of some of the different grease chemistries and kind of how they came about. The next thing worth talking about are the different NLGI consistency numbers. So where you would see this on a tube of grease would be this NLGI number. So in the hardware stores or auto parts stores, the two prominent consistency grades that you're going to see are the 1s and 2s. And so you might not have known, but there's actually nine different grades for the consistencies. How they're graded is this cone penetration, and then we've got appearance and kind of the food analogy. I used honey earlier when I was talking about viscosity, and so here you can see there are greases that can be as fluid as a cooking oil, and there are greases that can be as hard as cheddar cheese. And so in many of the firearm conversations that I've heard, people often say, you can't use grease, grease is too thick. And so just as I was talking about with the mineral oils, and one way to tell how they don't know what they're talking about is if somebody says grease is too thick for a firearm, ask them what NLGI number grease they're referring to. Probably look at you like a deer in headlights. So the 1s and 2s are again what's most prominent in the auto parts store and what you've seen the most. But we can have a variety of consistencies or thicknesses of the grease. The way the cone penetration works, and what you can probably tell by reading the words there, is they take a sample of the grease. There is a literal cone, and I don't know the angle of the cone, but there is a literal cone. That cone is then pressed into the grease, and then how deep that cone goes into it is how they're establishing the consistency or the thickness of the grease. What's important to note here is the consistency value. We use it to describe the grease, and it's often thought about much like viscosity, how we would purchase a liquid lubricant. But it's not the same. This is not really a measure of the grease's resistance to motion or flow. It's more the grease's ability to react a force. So the deeper the cone goes into the grease, you need more area to offset that force of gravity to support the cone. So although it's akin to viscosity, it's not exactly the same thing. For greases to describe their performance, we use a word called rheology. And so rheology is the study of quantifying the properties of the grease in relationship to temperature and shear rate. So the chemistry of the grease, not just the NLGI consistency number, is what's going to dictate more of that rheology property of the grease. So something to keep in mind and think about as we keep moving forward. Next thing we'll talk about a little bit are base oils. So again, back to our, call it our grease table. We've got our soap thickened greases, non-soap thickened greases. Most or all of these thickener chemistries can be made, or you can then make a grease with different base oils. So you can make a lithium soaped grease in a mineral oil or a group 2 oil. You can also make it in PAOs, and you can make it in many of the group 5 base oils as well. Some thickener structures I know can have difficulties with some base oils. I have heard about them, but they're not something that's like prominent in my brain right now. So I don't know, for example, a sodium thickened soap, what it doesn't react with or what it doesn't play with well. But it's important to know that the different thickener systems can be made with different base oils. And again, that comes down to the frustration of the consumer of what am I buying and what am I really paying for. We're going to keep picking on lithium soaps because they're the most prominent here in the United States. So I feel like they're probably worth talking about the most. Aluminum soaps, for example, are pretty far and few between. We will talk about them in my focused grease video because there's a lot of you guys that are probably lubricating your M14s and your M1As with a lithium soap or aluminum soap. So we will talk about them, but I'll probably pick on lithiums a lot. So lithiums, for example, if you're in the store and you're buying your lithium wheel bearing grease, or you're buying a fully synthetic lithium grease. So many lithium greases are going to be made with probably about a group 2 base oil. If you're buying a lithium grease that is a fully synthetic grease, they're actually going to be using a naphthenic base oil, so one of those group 5 base oils that is still derived from our dead dinosaurs. So there again, when we refine the crude oil, we've got our paraffin structures, our naphthenic structures, our aromatic structures, and the fourth one escapes me because I don't have my book to cheat off of right beside me. And so that naphthenic structure can be pulled off, and there are base oils made from that. The reason a naphthenic base oil is the more prominent or most likely if you're buying a fully synthetic lithium soap is because the way the structure of that base oil increases the yield of the thickener. So they're able to make more of the lithium thickener when they use a naphthenic base oil because there's reaction kinetics and it's advantageous and you get more product for cheaper essentially. So that's, something to note there. Is it good? Is it bad? It's probably neither, but it's something to keep in the back of your mind. So with our base oils, we picked on lithium. So now let's go ahead and pick on organoclay. And coincidentally, I actually have one of those here. So Mobile Grease 28, synthetic aircraft grease, clay thickener. So here, when you actually go to Mobile's website and look up this grease, we have our organoclay thickener, and the base oil that they use in this grease is a PAO. So they're using that group 4 base oil to create this grease. I believe this is a NLGI 2. Thought it said it on here. Maybe it doesn't. Maybe if I saw that when I looked it up. And so there, it's, kind of a red structure, kind of creamy to the touch grease. But so here, they're actually using clay that they've gotten from the earth. They mill it to a very fine consistency and powder, and they add the base oil and then any other additives that they need to add to the grease to get the performance and the properties that they need out of it. So PTFE, this will be the last one that we chat about a little bit because it's unique. So PTFE, you may be more familiar with its normal words or common word of Teflon. So PTFE can be both a thickener and it can actually be a base oil used in some greases as well. So that's kind of a fun one where it can really be a little bit of both. Here, we're on page 60 of the NLGI Grease Guide. So they've published a, in my opinion, very wonderful book that really walks through greases and explains them well. So here on page 60, they put some effort into actually taking pictures of some of the different grease structures. So here we have a lithium complex structure. Here's a lithium 12 hydroxystearate structure. Up here we have an aluminum complex, calcium complex. And it's fun, at least in my mind it's fun, to be able to see how the different thickeners in these different greases actually look different. And you can get different performances from different greases because of how that thickener structure is. So thought it'd be at least important to kind of show you that, again, not all greases are created equally, and they're not all the same. And the chemistry that goes into it does affect at a microscopic level what that grease is going to look like. Jumped the gun just a little bit there. So additives, we didn't talk about it much in our liquid lubricants, but additives can make up about 10% of our greases. And there's different additives that they add. A very typical additive would be some of the polymer additives that they would put in a grease. Most of the time, as a consumer, you would see that in like the tackiness and like the stringiness of the grease, because that really helps with water washout and water spray off in our industrial equipment. So they add polymers in to help keep the grease attached to the pivot pins and keep it in place, so that way the dirt, doesn't try to wiggle its way in, the grease doesn't wash off, and it stays in place a little better. Some solid lubricants. I'm sure most of you guys have seen like a 3% or a 5% moly grease. So molybdenum disulfide is a very common solid additive for greases. Anti-wear, extreme pressure, and rust inhibitors. Then we've got corrosion inhibitors, friction, antioxidants, structure modifiers as well. So the rust inhibitors are something that's important, again back to our firearm space, because rust inhibitors can be tuned for different environments again. If you're only worried about water, you can use one chemistry, and if you're really worried more about like salt water, you can use a different chemistry for that as well. And so that would apply back to our liquid lubricants as well. You can always tune a lot of these additives to get different performance criteria. Antioxidants, for example, help with the oil life, whether again be in a liquid lubricant or a grease. So as these products degrade in the machinery, they oxidize. And so just like our bodies, we drink a lot of pomegranate juice and eat a lot of blueberries for the antioxidant properties. They have to add antioxidants into our liquid lubricants as well so that they can last longer in the product. If you've ever played with grease, which I hope most people have. So here, again, you can kind of see some of that stringiness. You might have noticed that grease doesn't always perform the way you think it would. And part of that is because grease is what we call a non-Newtonian fluid. See if you can see it a little better there. All right, so now that I've got a little sheet of paper, one thing that we can see is if I pull my fingers apart very slowly, I don't get any of that stringiness that occurs. If I take my fingers and I move it very quickly, I have that string that develops between them. And so a little bit of what you see there is that non-Newtonian property of the grease. The other part of what you see there is some of the polymers that they add to greases to help with that tackiness, the retention, staying on the surface, and the water washout. So a little bit of that is our non-Newtonian. The other side of that are the polymers. So what do I mean when I say it's non-Newtonian? So a Newtonian structure would be like our liquid lubricants. So their viscosity does not change based on the stress that is applied to them. So when we were talking about the viscosity, so we're shearing the fluid, we're stressing the fluid, the rate that we stress that fluid does not change the viscosity. But with a grease, where's my grease? So with a grease, here we go. With a grease, there, it does change. So, two non-Newtonian fluids that you might be familiar with, one you're certainly familiar with, the other one maybe you're not, would be ketchup and the cornstarch and water mixture. So there you actually have two non-Newtonian fluids, or mixes, call it, that actually behave very differently. The cornstarch and water, for example, is a shear thickening mixture. So if you've ever played with it and you try to, punch it or, run your hand through it very quickly, it shear thickens. Its viscosity increases. There's even pictures of people running across large vats of cornstarch and water. So if you want to really ruin your YouTube algorithm, start looking that up. Those can be kind of fun. Ketchup, on the other hand, is what we call a shear thinning fluid. So ketchup bottles, at least in I think it probably started ending about the early 2000s, maybe the late 90s. They used to always come in the glass ketchup jars. And then they started packaging them, in the squeeze bottles and everything else. So if you took one of the glass ketchup jars and you're beating on the back of the bottle, the ketchup doesn't come out. You eventually hit the back of the bottle with enough force that the ketchup inside shears, and because it's a shear thinning fluid, you end up with this large of ketchup on your hot dog or your hamburger. So hopefully you've played with some ketchup and now you understand why it was so difficult to get out of the ketchup bottle and really why industry transitioned to the squeeze bottles. And you can still see a little bit of the shear thinning in the ketchup squeeze bottles when you put it on your hot dog. You squeeze it across, and as it's coming out the nozzle and piling, you see the little ripples and it looks very fluid. But then you can take your hot dog, turn it on its side when there's no stress applied to the ketchup, and it's not just going to drip off. So maybe next time you're at the barbecue, you're going to start playing with the ketchup, and, feel free to blame me for why you're doing that. So the non-Newtonian aspect of grease, and again, you can formulate it to get the different properties that you want to, but that's one of the reasons that it makes it a little more difficult to understand for most people, because it doesn't always behave the way you think it's going to. And so again, that non-Newtonian aspect can be quantified through the rheology measurements of the grease. And so there is a rheology tester where they can heat and cool the grease, and they can shear it at different rates, and they can do a lot of testing to develop curves to understand how the grease behaves, how it reacts, and how it rebounds. And with that level of understanding, you can really tune greases to get pretty exacting performance out of them. But again, most of what you and I interact with in our parts stores are not greases that have really been measured, or they probably have been measured, but they're not telling us that level of detail about the formulation, which is what part of the reason I think greases have a little bit of a bad rap in our firearm space, because we've been using greases that have been formulated for the pivot pins, the excavators, the wheel bearings. And in our fine firearms, the movements and reactions that we have in there are not really similar to those applications. So we've been using chemistries that were not designed for the firearms. So we don't necessarily have the rheology in the grease from our normal products that you find at the parts store. And so that's part of what I tried to narrow in on the grease that I sell was, again, I'm like you, I don't have rheology numbers, but I wanted to pick a chemistry and a formulation that I at least thought was more in tune and in line with our firearms, and not just an NLGI2 that you pick off the parts store shelf because it's a full synthetic and you think that means something and adds a lot of value, because this is not a full synthetic. I promise you that. All right, so if you've made it this far, we are now at the end of video number 2. So what I want everybody to remember as we finish up this video is not all products are created, well, we don't need to put that one there, are created equally. And just because something says oil, there's a large range of what the oil can mean. And just because somebody says grease, there are a lot of things that grease can mean, and the properties and performance that those products can have. And that's really what I'm trying to pass along there is, as consumers, we need to be smarter, and I'm trying to pass on some of what I've learned over the last year and a half now, I think it's been, reading these books and following people like Rafe on Lubrication Explained and Lake on the Motor Oil Geek. Because we're talking about it in other industries, but our industry of firearms, we're still just using CLPs and gun oils, and we're not really talking about what these products are and really why one product may be better than another. The next video that I'm going to focus on next is going to be greases, and so it'll probably be maybe the same length as this one. Maybe I can get it shortened down to less than an hour. Then we'll do oils, and then I'll start kind of talking about some CLPs and so on and so forth. So thanks again for watching. I hope you enjoyed it, and I hope you are now at least a little smarter consumer about what you're buying. Bye.